We are now going to start discussion on an entirely new topic, and this will be called the Laplace transform. Having studied so many transforms already, one might wonder why we need to look at one more transform. Now, this transform is for continuous functions, continuous time, and in certain ways can be understood as a sort of generalization of the continuous time Fourier transform. The continuous time Fourier transform attempted to represent both periodic and non-periodic continuous time functions using representing signals which were only periodic complex exponentials. So, the representing signals were always periodic complex exponentials in the CTFT case. We know that the general complex exponential given by x t equal to e to the power sigma plus j omega t, where the parameter of the exponential is a complex number, is also a preserved signal under linear time invariant processing. But so far we have not given any opportunity for a real component of the exponential to play any useful role. This is what we are now going to do. Now, so one way of looking at the Laplace transform is that it is a generalization of the Fourier transform in which the frequency is now allowed to be complex. Earlier it was allowed to be only imaginary, that is to say we had only j omega as the exponent. Now we are allowing sigma plus j omega. So, that is one way of viewing the Laplace transform as a generalization of the Fourier transform. But more importantly, we know that the Fourier transform had a certain limitation. The Fourier transform existed only for signals which were absolutely integrable or summable, integrable. So, the Fourier transform existed only if this was true. So, if the absolute integrability was not assured, then probably the Fourier transform would not converge. This is what we were faced with. What we are now going to do is to see if by modifying x t in some manner, we can make an x t which was inherently unable to meet this criterion into one which can meet this criterion. So, this is the second way of looking at the Laplace transform as a means of generating the Fourier transform of a modified signal and studying it for different levels or different degrees of modification. So, modify time signals x t and study the existence of its of the modified signals continuous time Fourier transform for different degrees of modification. Extents of modification. So, let us give the definition. The Laplace transform of x t is written as x s, and it is defined as integral minus infinity to infinity x t e to the minus s t dt, where s equals sigma plus j omega. So, what we get in the transform domain is a function of a complex variable. Earlier we had only a function of an imaginary variable if we looked at j omega, or a real variable if we looked only at omega. But being s now being a complex number, there are two variables which can change independently, sigma and omega. Thus, x, capital X, is actually dependent on two quantities, sigma and omega. This means something drastically new has happened. We can no longer really plot the Laplace transform of a function x t like we plotted the Fourier transform spectrum of the same function, because now it depends on two variables. So, what we have is a plot of two independent variables, a plot that depends on two independent variables. It is what we call a 3D plot. Thus, x s requires two dimensions for the independent variable. Furthermore, x s itself can be complex. So, at each point s equal to sigma plus j omega, x s will have a real part and an imaginary part, or a magnitude part and a phase part. Hence, we would actually get two 3D plots, the real 3D plot plus the imaginary 3D plot, or the magnitude 3D plot plus the phase 3D plot. Thus, we require to make two 3D plots, a real part 3D plot, real x s versus sigma and omega, and imaginary x s versus sigma and omega. So, this gives us a picture of what to expect. With this introduction to the Laplace transform, let us now see what we can say about it next. This much is about the Laplace transform. We will see, if we write the expression for it as we have done just now and try to interpret it as a Fourier transform, what actually happens. X s equals x of sigma plus j omega, and this equals the integral minus infinity to infinity x t e to the power minus st is actually e to the minus sigma t e to the minus j omega t dt, which can be looked upon as the Fourier transform of this function. That is, this is the Fourier transform of xt e to the minus sigma t. While this just seems like an interpretation, this will form the basis of our perception of the Laplace transform throughout the discussion. This will be the most convenient and easy way of trying to understand the Laplace transform. So, I will start the rest of the discussion by prefacing it with a brief review of how e to the minus sigma t behaves for different values of sigma. Let us make a plot. One point is sure, e to the minus is greater than 0 for all t and all sigma. This is a point that is worth observing. Thus, absolute integrability of e to the minus sigma t is the same as the integrability of e to the minus sigma t. Now, let us make some plots for different values of sigma. Let us take this point as 1. Okay. Now, suppose sigma is greater than 0. If sigma is greater than 0 and you plot e to the minus sigma t, for positive time we know that it is a decaying exponential, which means that for negative time it is a blowing up or growing exponential. So, we can make a plot that goes like this. This is for some value of sigma. If you choose a smaller value of sigma, that is to say sigma is greater than 0 anyway, but we are saying choose a value of sigma closer to 0 than this one, then you will have an exponential that is closer to flat. That means you would have on the positive time something like this. So, this we will call sigma 2, this we will call sigma 1, then we have sigma 1 is greater than sigma 2, this much we know. Now, let us make another plot where sigma is actually equal to 0. Just a flat horizontal line that is given as that is equal to 1 for all time. Okay. Then suppose sigma is less than 0, but small, that is mod sigma is small, but sigma is negative. Then you will have a function e to the minus sigma t which rises for positive time and is decaying towards negative time. So, you get a curve that looks like this. We call this sigma 3. Next, if you make a large negative value of sigma, that is sigma 4 less than sigma 3, then you will have something that rises faster in positive time and slower in negative time, and falls faster in negative time. So, we have if this is sigma 4, then we know that sigma 3 is greater than sigma 3 is greater than sigma 4. We know this. So, these are various plots of e to the minus sigma t for different values of sigma. Now, the argument goes as follows. Suppose x t is causal. That means to say x t equals 0 for t less than 0. Only towards the right it has non-zero values, towards the left of x equal to 0 it has 0 values. And suppose that the f t of x exists. That is to say, suppose that this is valid. It is absolutely summable, absolutely integrable. When it is absolutely integrable, then let us see what we can say about e to the minus sigma t x t. If e to the minus sigma t x t is to be absolutely integrable, that means the product should have an area that does not blow up. Thus, if we have some value of sigma for which this is the case, sigma 1 for which x t e to the minus sigma t sigma 1 t is integrable, I mean of course is absolutely integrable, I think I will abbreviate this to A I. Absolutely integrable we will say is A I. Then it is evident that for any sigma 2 greater than sigma 1, the absolute integral of x t e to the minus sigma 2 t will be less than the absolute integral of x t e to the minus sigma 1 t. Correct? Because this decays faster in positive time. That is evident if you look at these pictures, this function versus this function. Clearly, that is this function is falling faster in positive time than this function, and x t is causal. So, when it falls faster, the area of the under the product will be less than it was for the case of sigma 2, except that here we have chosen sigma 2 greater than sigma 1, here we have chosen sigma 1 greater than sigma 2. So, let us not confuse this sigma 1 sigma 2 with this sigma 1 sigma 2. Okay. Hence, if the L t of x t exists it exists for sigma 1, it will also exist for every sigma 2 greater than sigma 1. That is an interesting point to observe. All right. So, this is the way we proceed. We look at some function x t and see if there is any sigma for which x t e to the minus sigma t has a Fourier transform. If it has a Fourier transform, then we will say that x t has a Laplace transform for that value of sigma. Now, the very terminology turns out to be different. In the case of the Fourier transform, it was a do or die kind of situation. Either x t has a Fourier transform or does not have a Fourier transform. For the case of the continuous time Fourier transform, x t either has a transform or it does not. Or it does not. It was just make or break, black or white. Whereas with the case of the LT, it turns out that there can exist certain values of sigma for which the LT exists, other values of sigma for which the LT does not exist, and that is how it is. The set of points of sigma for which the Laplace transform does exist is called its region of convergence. Is called its region of convergence, abbreviated to ROC. All right. So, this is where the Laplace transform fundamentally differs from the Fourier transform. It has to make a record not just of what the Laplace transform of x t is, what value it is, but also where those values are valid, what points of S are those values valid. Now, to make things more graphical and easy to picture, we make what are called S-plane plots. S-plane plots essentially are plots of the plane sigma omega, where sigma is on the horizontal axis and omega is on the vertical axis, and the S-plane plot of xs divides the S-plane into regions over which xs exists or fails to exist. So, in some regions xs will exist, in some other regions xs may not exist, may not converge. So, this is called an S-plane plot. Example, for x t equals e to the minus a t u t, which is just like the causal example we have just dealt with. This is also a causal example. Then e to the minus a t is some kind of a curve. E to the minus a t is some kind of a curve which depends on the value of a. So, there is no point plotting that curve. What we will do instead is to understand its Laplace transform. E to the power minus a t u t has a Laplace transform x of s equal to integral minus infinity to infinity e to the minus a t u t e to the power minus s t dt. That is equal to, because there is u t over there, 0 to infinity e to the power minus a minus sigma minus j omega t dt. This can be rewritten as summation from 0 to infinity e to the power minus a plus s into t dt. Right. Let us assume that this integral converges. If this integral converges, then its integral will be e to the power minus a plus s times t divided by minus a plus s evaluated from 0 to infinity for t, and this comes out to be equal to 1 by s plus a. But in order to assume that it converges, we have to see for what values of sigma this integral will actually converge. Now, the real part of e to the power s plus a the real factor of e to the power minus s plus a times t is e to the power minus sigma plus a t e to the power minus j omega t. This is what we have. Now, you see, e to the power minus j omega t is not integrable, because both its real and imaginary parts have finite power and not finite energy. They are not integrable. That is the end of the e to the minus j omega t. So, any hope we may have of excess existing will rest with whether this is a decaying exponential over the interval of integration. That means, e to the power minus a plus sigma times t must decay over positive time. So that when multiplied by something like e to the minus j omega t, which has finite power and not finite energy, the product will still have finite, will still be absolutely integrable. Okay. Now, let us see what this means. This means that a plus sigma must be greater than 0, or that sigma must be greater than minus a. In fact, sigma must be greater than minus a defines the so called region of convergence. This is the region of convergence of xs given by 1 by s plus a. Fine. So, this formula is valid only for this interval of the S plane, this part of the S plane. Thus, it is clear that unlike the days of the continuous time Fourier transform, where we merely needed to take a record of the algebraic expression for x of omega, now every time we find the Laplace transform of some x t as x s, we have to note the expression for x s as well as the region of the axis, the region of the S plane where it is valid. Thus, in the example just concluded, we see that it is only for sigma greater than minus a that x s equal to 1 by s plus a is valid. So, the Laplace transform consists of two parts, consists of two items of information. The expression, one is the expression for excess, and 2 the region of convergence. The region of the S plane where the expression holds. All right. Now, let us just see what happens if we consider the Laplace transform of two functions simultaneously. That means, of the sum of two functions. Consider x t equals e to the power minus 2 t u t plus e to the power t u t. From the form of the Laplace transform equation, it is clear that it is a linear transform. So, that the transform of the sum of two functions must be equal to the sum of the transforms. On this basis, and knowing the Laplace transform as we have just experimented with it for this expression and this expression separately, we can write that x s equals 1 by s plus 2 plus 1 by s minus 1. So, we can write this, but then there is the issue of the region of convergence. Now, since we cannot directly comment on the region of convergence of the entire x s, let us look at the regions of convergence of the individual parts. For this part, clearly if you go back to the original function e to the minus 2 t u t, we find arguing analogously to what we had earlier, that 2 plus sigma must be greater than 0, that means sigma must be greater than minus 2. Sigma must be greater than minus 2 is what this expression requires. Now, what does this expression require? It requires by similar arguments that sigma must be greater than plus 1. So, in the S plane, suppose we make plots of the region of convergence of the first component function and of the second component function. So, for one of them it is this, for the second one it is this, and for the first one it is this, sigma greater than in both cases. So, it is this. This is what we get. So, if we ask now what is the region of convergence of the combination, then the answer is clear. If x s will converge, if each component of the sum separately converges. That is to say that we have to look at the intersection of the convergence regions of the two terms, which comes out to be, if I call this R 1 and if I call this R 2, then it comes out to be R 1 intersection R 2, which is just equal to R 2. So, R 2, where R 1 is this, let me just denote this in a more friendly way. using different colors. So, let us say that this is R2 and this is R1. So, R1 is in green and R2 is in blue, and R1 intersection R2 is the part which is hashed both by R1 and R2. So, this is what we get when the Laplace transform of a sum of functions for each of which the Laplace transform and the individual regions of convergence are known. Now, let us introduce ourselves to a rather surprising fact. Let us consider x t equal to e to the power minus a t u of minus t. This is a function which is what is called left sided. That means that for t greater than 0 it is 0, for t less than 0 it is non-zero. So, this is e to the power minus a t u t. Now, let us try u minus t. So, let us try to find x s equals integral minus infinity to infinity x t e to the minus s t dt, which simplifies along lines similarly earlier described, that it becomes minus infinity to 0 because that is the area of non-zeroness of the argument, e to the power minus a t e to the power minus s t dt, which after simplification comes to 1 by minus 1 by s plus a with a region of convergence that requires that sigma plus a must be negative. That means sigma must be less than minus a. So, this is the definition of this describes the ROC for this function. Sigma must be less than minus a, and then the algebraic expression is that x s equals this. Now, this looks familiar, the expression looks familiar. In fact, since the Laplace transform is linear as is evident from inspection, you will see that if e to the power minus a t u of minus t goes to minus 1 by s plus a, then minus e to the power minus a t u of minus t must go to 1 by s plus a. But if we recall that e to the power minus a t u t went to 1 by s plus a. We solved this a few minutes ago. This means that two totally different functions, namely this and the second one being minus e to the minus a t u minus t, also go to 1 by s plus a. This seems to suggest that unlike the continuous time Fourier transform, x s is not unique. Different functions x t can have the same Laplace transform. That is not really true, because recall we have said right a little while ago that the Laplace transform of a function has two items of information. What we are now trying to do is to ignore the second item of information. What we have written down here is only the first item of information, which is the algebraic value, the expression for x of t, for x of s. We should also note that for this function, the upper one, sigma must be greater than minus a, whereas here sigma must be less than minus a, as we just found. That means that though the expressions are the same, the regions of convergence are different. This is what helps us distinguish between the first xt, which I will say, I will call this as x1 t and x2 t. x1 t is this and x2 t is this. Their expressions are the same, but the regions of convergence are different. So, as long as we take both items of information into consideration, the Laplace transform does remain a unique map from xt to xs. Okay. Now, with this in mind, with this in hand, we will see what more we can do to learn about the Laplace transform. Let us start with a few examples. Now, the fact is that for our purposes of use, it is sufficient to consider Laplace transforms only of certain standard functions which are related to the exponentials. Thus, we will consider, for example, we have already done e to the minus a t u t and e to the power minus e to the power minus a t and u minus t. For these functions, we already have the Laplace transforms. Now, we will consider, I will not solve these in detail, but we will consider cos omega naught t u t. This comes out to have a Laplace transform of s by s squared plus omega naught squared with sigma greater than 0 as the ROC. Sin omega naught t u t comes out to have a transform omega naught by s squared plus omega naught squared for sigma greater than 0 again. These are just a listing, this is just a listing of the standard forms for which we look for Laplace transforms. Next, suppose you had e to the minus a t cos omega naught t u t, that would give you a transform of s plus a by s plus a whole squared plus omega naught squared sigma greater than minus a, and similarly e to the power minus a t sin omega naught t u t would have a transform of omega naught by s plus a whole squared plus omega naught squared sigma greater than minus a. Suppose we had t to the n minus 1 by factorial n minus 1 e to the minus a t u t. This would give us a Laplace transform of 1 by s plus a to the power n sigma greater than minus a. So, these are the general forms in terms of which most of the other simpler expressions for which we look for Laplace transforms will be created. Okay.